And our first talk is going to be an invited talk by Tilman. And I'm very excited for that because he told me it's going to be interactive and we worked on that together. So that's, yeah, I hope we start off with a great talk. And yeah, unless there are any really pressing, immediate questions or comments from my co-hosts, I would say, take it away, Tilman, and have fun at this conference.
Okay, thank you very much, Anna, and good evening from Tokyo to everyone. It's a great pleasure, it's a great honor to open this exciting conference. So thanks a lot for the organizers, for, well, the organization, and for having me giving this overview of the first stars. And I have to admit it's challenging to summarize this broad topic in about 20 minutes, but I will try my best. So first, a small, motivation and introduction why we actually care about the first stars. And so for those who are already in the field, that's more a reminder. For those who are new to the field or students, that's the motivation. And I would say we should care about the first stars because, well, they set the scene for everything that happens afterwards. So they shape the first galaxies. Their radiative, chemical, and mechanical feedback basically sets the scene for galaxy formation. And the first stars may provide the seeds for the first supermassive black holes, and they provide the first heavy elements. Now, their contribution to all these feedback channels depends on their stellar masses. And the initial mass function of the first stars, which exactly quantifies the distribution of stellar masses of the first stars, is largely unknown. This is because, well, the first stars, they are too far away in space and time, so we cannot observe them directly, and we only have indirect constraints from observations and simulations. And so that's just a qualitative illustration. So we should care about the first stars and better understand them so that we can better judge what is exactly their contribution to these feedback mechanisms. Now, we will come back to the IMF, but let's first ask the question, under what conditions do the first stars form in the early universe? In what environment? And usually the condition, as always for star formation, is you need to have cold gas. In the early universe, the only main coolant is molecular hydrogen. So the condition is you need to build up a halo that is massive enough to contract gas so that you can then, well, form molecular hydrogen and cool down. That is usually quantified by the critical mass. And here we see a function, or this as a function of redshift. And I would like to draw your attention to two recent studies by Anna Schauer in blue and Mihir Kulkarni in green. These were the first simulations that both included Lyman-Werner and baryonic streaming. These are both effects that we think they will delay and suppress POP3 star formation, or, well, delay or even suppress. And so if a halo is above this threshold, it is expected to form POP3 stars. And the interesting thing that I find here is this discrepancy, especially at high redshift, of about 1 order of magnitude. And I will not go into this now because Mihir Kulkarni will later give a talk on, I think, this topic. So we can look forward to this. But I think roughly we can say, well, the first stars form at redshift maybe above 10 to 30 in mini halos around 10 to the 6 mass, 10 to the 6 solar masses. Now, coming back to the POP3 IMF, and now comes the interactive part where I need your help. So I called this the democratic initial mass function, and I will launch a poll in Zoom. And the question is simple. The standard POP3 IMF contains stars of which masses? So it's a multiple choice poll. You can select your the mass range that you think the first stars would, well, inhabit. You should see the poll now. I will give you some time just to explain what I mean with the standard POP3 initial mass function. So we know that POP3 stars, if there is a strong Lyman-Werner background, then we may form supermassive stars instead. And so that's not what I mean. So the standard is in isolated halos without external feedback. And just realized probably the hosts and co-hosts cannot poll right now, but I'm seeing already 20, 25 people. I will wait a bit so that this can grow. It's a beautiful histogram already. All right, I can also on my, wait 1 second, let me just do this. Okay, 50, and right, not everybody has to submit their answer. So if someone thinks, well, I don't know enough, then we can wait. Okay, we should not do this for too long. Already 70% of people have replied. I will give you 5 more seconds because it goes from my precious time. Okay, I will end the poll and I will share the results, and I will also try to make a screenshot that I don't forget it. And I think now you should see the results. So this is our democratic POP3 initial mass function. I will not comment on it now. I will make maybe a nice figure out of it and put it on Slack. And it would be interesting maybe afterwards to do this poll again if we have time. Let's see. But for the moment, let's go back to my presentation. So that was the, it's loading. Yes, that was the democratic POP3 initial mass function. All right, maybe, sorry, you have to close the poll if it's still open on your screen. And so that was the democratic. And now let's see what the simulations have to say on this same topic. So I like this form of overview. What I show here is the expected mass range from various simulations as a function of the year of publication. You may have seen a similar plot from me before, but I have updated it with some new results. So this is more qualitative, the mass range. And what we see is kind of a decrease over time, which I would assign to a better numerical resolution in the simulations, so that around 2010, people can actually resolve the fragmentation of smaller clumps. And well, I think later we will hear also talk by Sugimura-san, and he may tell us what's special in his simulation. But roughly, we still see a scatter, and I would not say that this has converged yet. So this is still open for improvements. And it's maybe also unfair, some of these comparisons, because these are just different simulation codes and different physics included. So to have an overview of exactly the physics included, this is a really nice compilation done by Piyush Shadar, and I just added a few information where he compared different 3D simulations of POP3 star formation and the different physics that is included. So AMR, adaptive measure refinement, that's the simulation technique, if the chemistry is followed, if turbulence is resolved, if magnetic fields and radiative feedbacks are included, and then if fragments evolve in this simulation. So what you can see, well, first is a large diversity. And interestingly, at least these criteria defined by Piyush, non-simulation or no simulation so far has included all these. So there's still room for improvement. However, it's always easy to say from the simulation side, hey, we need to improve the physics. And yes, we need, but what else do we need to do? And especially, I think one problem is the time that we need to push the simulations. And on this, Hachime Souza last year made a very nice, almost a meta study. So he came up with some scaling relations between the time and the threshold density that allows us to compare different simulations of POP3 star formation. And what we see here is the number of fragments as a function of time after the first protostar. And so what he shows is also analytically that there is some power law relation to the power of 0.3. And most simulations with very different codes and approaches follow this relation. But now the question is, for how long do we have to simulate? And the argument is that roughly after 1,000 to 10,000 years, we would expect protostellar feedback to terminate star formation. So to prevent the formation of new clumps and to stop accretion onto existing clumps. So I would say, and Hachime Souza would say, we would need to simulate roughly 1 order of magnitude longer so that we actually see a convergence of the mass distribution. Now, these were the constraints from numerical simulations. In the next few slides, I want to highlight what we know from observations, the indirect constraints, and I think the most important one is stellar archaeology or extremely metal-poor stars. The idea here is these extremely metal-poor stars, they have formed in the early universe, and then they have conserved their chemical composition until the present day. So if in the present day universe we see these old metal-poor stars, we basically see the fingerprint of POP3 supernovae. And so what we can then do is we take the chemical composition of these old metal-poor stars and we compare it to what we think are the supernova yields of the first stars. And this, what we see here, is a study by Miho Ishigaki. And what she did is she took a sample of around 200 extremely metal-poor stars and did exactly this matching of progenitor supernovae. And what she finds is this distribution. The different colors are different explosion energies. And it roughly clusters around progenitor masses of 25. And while I think this is very informative and one of the most complete studies of this kind, it's of course very limited and biased, because with this method, we can only probe the mass range where we expect the chemical signature, which here is the core collapse supernova range. And for example, but that's a different issue, so far we have not detected the chemical signature of pair instability supernovae. So, another thing that metal-poor stars can tell us is about the POP3 multiplicity. And there will be also a talk by Louise later, and she also had a paper on exactly this just yesterday, so you should all check it out. However, the figure here is from myself and Miho Ishigaki. What we did here is with supervised machine learning, we took 500 metal-poor stars and classified them depending on the number of enriching supernovae. And so these are the bins that you can see here from 1 to 5. And we would claim that the number of enriching supernovae corresponds to the number of POP3 stars, or POP3 supernovae per mini halo. And so what we find that most of them are mono-enriched, so just enriched by one previous supernova, but we see a tail of multi-enriched, extremely metal-poor stars. And so this allows us to investigate the POP3 multiplicity. And to you, this may look like a simple histogram, but this is like 2 years of hard work, and we hope that we can finish the paper soon. So there will be further talks also later on the POP3 binary statistics, which are of course related to multiplicity. And the last point, what extremely metal-poor stars can reveal about the first stars is on the low mass end. And here the idea is, if the first stars are, if their mass is less than 0.8 solar masses, then they should survive until the present day. And we should see them as metal-poor stars. And so this is a study by Mathis Mack, which shows the probability of not detecting metal-free stars in the Milky Way as a function of the Milky Way halo mass. So this dimension is just because we're not exactly sure. So they've done several realization of Milky Way-like merger trees. And other people have done this before, but the new insight from Mathis is the following. Instead of asking what fraction of all stars in the Milky Way could be POP3 survivors, his insight was, well, finding POP3 survivors, it's the same strategy as finding extremely metal-poor stars. And so it makes more sense to compare what fraction of extremely metal-poor stars should be metal-free stars. And with this, he can get very tight constraints on the survival. And basically, the bulk of these points is below 1%. And ultra metal-poor stars are more constraining than extremely metal-poor stars. But basically, from here, we can conclude with 99% credibility that there are no metal-free stars that have survived until the present day. So this was stellar archaeology and metal-poor stars. Now I have one slide on further constraints. I said 20 minutes is tough to summarize everything. So let me just mention what else is possible. For example, gravitational waves could show us, and maybe are already showing us, some idea of the remnants of the first stars. Then a super exciting paper by Anna Schauer on the ultimately large telescope, an infrared telescope with a 100 diameter dish on the moon that could eventually ultimately find the first stars. or the 21 centimeter signal, where we need some additional heating, cooling to explain this, which may come from the first stars, or the direct detection of supernovae at high redshift, and a long list of other constraints. However, I would argue, and I'm happy to discuss later, so far these are mostly non-detections or upper limits. And so therefore, I would say it's not further constraints at the moment, it's more like future constraints. Because we need either, well, new facilities to detect those, or like for the gravitational wave, we need maybe 1 or 2 more decades to have some statistics to see different populations in the black holes. But still, it's interesting to see the effect that POP3 stars could have on these observables. Now, on the last 2 slides, let me allow a bit of self-advertisement, but it's of course also in the spirit for the community. I want to mention A-SLOTH, which stands for Ancient Stars and Local Observables by Tracing Halos, which I think is also not the worst acronym in astronomy. And A-SLOTH is a semi-analytical model of star and structure formation. And the model mostly focuses on the first stars, second generation stars, extremely metal poor stars, but can simulate down to redshift 0. So if you want to know more technical details, either contact me or look at these papers from my collaborators on this project. And just one slide on what A-SLOTH can do for you. So A-SLOTH usually operates on megaparsec scales. So for example, we can simulate Milky Way-like galaxies. And if you now have a simulation on much smaller scales, so if you simulate POP3 star formation, really the fragmentation, or if you have a new seeding scenario for supermassive black holes, or if you have a new table of yields of the first supernovae, you could implement those into A-SLOTH and then see what is the effect on large scales. What are the statistics, or how likely are those conditions to be realized under cosmological conditions? On the other side, if you have large cosmological simulations, which do not allow sufficient resolution to resolve, for example, the formation of the first stars, then you could also use A-SLOTH as a subgrid model and either tabulate or run it in parallel. And so A-SLOTH could help you with your subgrid physics in bigger simulations. A-SLOTH is semi-analytic, so it's quite fast. It's parallel, and so therefore it's also good for parameter exploration. And we hope that we can make it public in a few months. We're working on it. So that brings me to my last slide, to the conclusion, to the open questions. One could condense it to 2 open questions. That is, what is the critical halo mass for POP3 star formation? And maybe Mihir will talk about this later. And what is the POP3 IMF? However, the second question, we can maybe add a few more details. So from the POP3 simulations, I think we need to run for longer. And if we believe Hajime Souza, we need to run roughly 10 times longer than what we're doing right now. And we need to add more physics, or simulations need to be self-consistent, for example, with magnetic fields and feedback. And then I would say, and I'm happy to discuss, that stellar archaeology at the moment is the most informative observational constraint that we have. And for example, stellar archaeology allows us to say that there are no metal-free survivors. If this means no POP3 survivors, it's a different question. So still room for additional research. Then the multiplicity and the binarity of POP3 stars. So I and Louise have provided some first hints into this field from the observational side, but still not the final word. And one thing that I have not spoken about in detail are parent stability supernovae, which are theoretically a very robust prediction. But where are they? We haven't seen their chemical signature, and not, at least not convincingly, or their light curves. And so there is still a lot of work to do. I hope a lot of exciting work to do. And I'm looking forward to the remaining talks, because they will cover some of these and maybe show the recent progress on these open questions. So that's from my side, and thank you very much. And we have more time for questions.
Thanks a lot, Tilman. This was a great introduction into the topic. Please, everyone, stay muted and post your questions on Slack, and I will read them out. We have a very first question already by Stefan. It says, regarding the plot of critical halo mass versus redshift, what happens if you to higher redshift? Can you convolve the redshift evolving halo mass function to get star formation rate versus redshift?
So the question, sorry, because I was dealing with things, was what happens at higher redshift, and can we convert this into a star formation rate density? Yeah. Yes. Right. To answer like what happens with these functions at higher redshift, I would rather refer to Anna or me here, who could answer this better. The idea is basically, I mean, you need a minimum halo mass. And also these are, one has to say, these are extrapolations. So I just know, for example, Anna had only halos in a certain redshift range, I think around 14 to 24, well, whatever. But here, 3040 definitely is extrapolated to higher redshift. And also the baronic streaming at this high redshift would be even stronger. So maybe they even would go up. So right, I cannot say exactly what would happen with these functions. But now for the star formation rate, yes. It's probably not an easy conversion because there is feedback. And I think that's also what Eli and Micha will talk about later. But in principle, this convolved with some halo mass function allows us to derive some star formation rate density at high redshift, something that A-SLOTH can also do, for example.
Awesome. Then Naoki is asking, SUSA plot is showing increasing number of small fragments and the constraints on the fraction of low mass population 3 stars can't be easily made consistent. So I think the question is, apparently there's a tension, and what your thoughts are on that you cannot really combine this work from SUSA with a low mass population 3 star constraints.
Okay, good point. So the point is that if the extrapolation is true, then maybe we expect dozens of POP3 fragments, and then it would be likely that some of them are low mass, and that is in tension with the no metal-free survivors. Okay, if I correctly summarize the question, and I agree, that would be a tension, and therefore I try to emphasize that their survival is for metal-free stars, not for POP3 survivors, no metal-free survivors. And so there is another discussion about possible pollution. So it could be that the first stars have low masses that form in the early universe, and then their surface is polluted with metals from the ISM. So we would not see them as metal-free survivors. Right, I don't know if this solves the tension, but maybe at least it mitigates the tension.
That's a start. Gen says, great talk. In your new results with Miho, you compared the sum of elemental abundance with the observed stars. If so, how is the statistical noise in the 5 population 3 stars case?
A statistical noise in the 5s on this highest bin. So I don't know if that's exactly the statistical noise, but definitely there are very high degeneracies. And that's also, so this NA bin is exactly the ones where our classification is just not reliable enough. We have checked that there is no bias. So even if we change the threshold, the relative height of these does not change. But right, to discriminate an extremely metal poor star that was enriched by 4 supernovae or by 5 supernovae, it's really just statistical minor significance. So, right, there is scatter or at least uncertainty, which we try to quantify in this been, but at least the qualitative message is not affected by this.
Okay, awesome. And we have a last question by Zoltan. How sensitive is the ULT on the moon? Say, what is the mass of a POP3 star cluster? What is the mass of a POP3 star cluster at redshift 10 that it can detect? Shall I just answer that?
Please, yes.
So we designed it with reference to Angel et al. 2008, so that we have a fiducial mass of 1,000 solar masses. It can reach down to a little bit lower than that. It depends on the IMF. So I would say the lowest mass end is roughly 500 solar masses, depending on the IMF. But it's designed for 1,000. Okay. I think we have, Tilman, please check out the Slack. I think now more questions are coming in, but for the sake of keeping this in time, I would say thank you again so much, and let's move on to our next speaker, Shingo.